as follows. Right. Now this isn't perfect the way it's written, but we'll deal with it. Okay. So the value of the, we know what's going on at the starting point. So y0 is our 1, and there's no error there, that's fine. Okay. So now the next y value. So the true solution at 0.5 is approximated by y1, which is the previous y value. The previous y value at this point is 1. Now the only thing I don't like here is the way I've written it. I have slope times step size, whereas here I have step size times slope. Perhaps you can swap those around. So here's the step size I have, and then you calculate the slope at the previous point. Now the slope is given by this, and the previous point, well, maybe we'll just write something down here actually. So at this point, at this initial point, you have x is equal to 0, y is equal to 1 here. And so what we're doing is we want to calculate the slope here. So we put in the x equal to 0 and the y equal to 1 into this. Now there's no y dependence, so the 1 doesn't matter. We just plug in, substitute in x equal to 0 to this, and we find that the slope at this point, the previous slope, is 8.5, and we get out an answer of 5.25. Now that is an approximation to the true solution at 0.5. So we might just write that here. So at 0.5, we estimate that the exact solution of this is 5.25. That is there. Now what we want to do is we want to jump off that approximation to figure out what's going on at 1. So the next value of y, which is the value which approximates the exact solution at 1, is the previous y value. The previous y value is 5.25 plus the step size times the previous slope. Now at the previous point, the x coordinate is 0.5, so we substitute into that to get the previous slope. So I put in x equal to 0.5 into that. So I have previous y value, step size times slope, and we get 5.875. And that is an approximation to the exact solution at x equal to 1. Now obviously we could go like this all day. We can use, however, an Excel worksheet or VBA to kind of keep on going, and that's what I did here. So how did I do this? So we've gotten to here by hand. So then I would have said, okay, the next y value, this thing, is the previous y value, 5.875, plus the step size, which is 0.5, times the slope, which is the dy dx. Evaluate the previous point, so I put x equal to 1 into that. Out pops this number. And I just keep doing the same. This is the previous y value plus step size times previous slope. This is the previous y value plus the step size times the previous slope. And it's good the way I graphed this with straight lines. So the true solution might be perhaps something like that. And this is an approximation to it. Okay. As it happens, solving this differential equation by hand is unnecessary. It's quite easy. You could, if we looked at it again, you don't need to do any fancy separation of variables or anything like that. You can simply anti-differentiate both sides. You anti-differentiate the derivative, you get y of x, which is what you're looking for. What will this give you? Whatever. Minus a half x to the 4 maybe. This will give you something like 4x cubed, minus 10x squared, plus 8.5x, and of course there could have been a constant there. So you have to find that constant, and it's not that hard, because if you substitute x equal to 0, you get y equal to 1, which I think means that the constant has to be 1, which we do that. So this is you get from anti-differentiating, and then substitute the initial condition in, you find c. Now, if you can get the exact solution, why would you look at the Euler method? That would be stupid, I agree, but we want to show kind of how the error works, and we want to picture what's going on. So what we have here is our Euler method approximations. So these are our yi approx, joined up with straight lines, and then we have the exact solution. Now, is this exactly the solution? I'm not going to worry too much about that. Excel has kind of filled in the dots, but let's assume it knew exactly how to do it. So this is the y exact. So this would be the y values at the various x values. Certainly these points here are correct. Maybe in particular we might just look at the points at 2. So at 2 the approximation is 4.5 and the exact solution is 2. Now obviously that's a diabolical error. Now I don't mean that we haven't done anything wrong. It's just the numerical method isn't precise enough. It's not accurate enough, sorry. The precision isn't the problem, it's not accurate. So here we see the yi approximate the y of xi, but not very well. As we can see from previous graphs, if we move too far away from a point, so for example here, because I've used Excel rather than a graphing thing, there is a discrepancy between these two slopes. The true solution would probably look something a little bit more like this. What I want you to do is go from this point to this point and make sure that this is actually the tangent. So how you do that is start here and drive off, going in the direction of that straight line and then turn around. Something like that. Yeah. Ooh. Yeah. Okay. So what I'm saying is that this is the tangent to the exact solution, and it's accurate, but we can't go too far away before it becomes inaccurate. So what we have to do to track the true solution better is that we must change direction more regularly. Like here, even if we change direction at maybe 0.25, we probably wouldn't be too badly off. Of course, you can get the general gist of the thing, but really this is very, very inaccurate. So if you want to change direction more frequently, what you have to do is reduce the step size, which is the same as increasing the number of steps. And remember, we're just staying between 0 and 4. So if you reduce the step size, you have more steps. If you have more steps, you're reducing the step size. So we did some of these in Excel. Now obviously you can't really do these by hand. So here we have two graphs. So the same problem, when I say the same problem, I mean the same differential equation. I suspect that the one on the bottom here is the exact solution. And the one on the top is our Euler approximation. That is with a step size of 0.1. And on the right hand side, you can see that the errors go very, very small. That's with a step size of 0.01, which means we had 400 steps. Now, theoretically, that might eventually cause problems for our computer, but it's okay at the moment. You can see on the left-hand side that you pick up a lot of the error and you never kind of really get it back exactly. So most of the error occurs around here. You don't really pick up much more here. We'll talk about that a little bit later on. Okay, now what we want to do really is now to analyze these errors, and I need some language that you don't have. So I need to talk about a little bit about Taylor series and something called big O notation. Okay, so the O here stands for order, and we kind of see a good example here, just a it's actually not a good example, but anyway, just to start thinking about it, about how this is it's just a rough way of looking at things. Rough, very useful, but rough. So if you had a bank balance like that, so that's €1,000,000, 2,098 euros and 21 cents. How much money would you say you had in the bank? You'd say you have 1,000,000. You wouldn't say I have €1,000,000 and 2,000. That'd be a bit stupid. So a bank balance like this, you'd say, is of the order of 1,000,000. Now at the moment, that's a very rough thing. It kind of says it's approximately. Later on, order will mean something. Oh, we're about to go to it now. On the one hand, this means that you've roughly 1,000,000 in your account. However, something like 2.5 to 3 million is also considered of the order of 1 million. Roughly, anything that is a multiple, say, of a million, and when I say a multiple, you're maybe thinking of everything from maybe a half to 10 is said to be of the order of it. So for example, the time taken to brush your teeth is of the order of 3 minutes. It's probably a multiple of 3 minutes. In fact, that could be 1 minute. So it'll be the order of 1 minute. We'll change that for next year. Everyone brushing their teeth are doing it for probably between half and 5 minutes. It's a multiple of a minute. The width of a pencil is of the order of 1 centimeter. Okay? When you order takeaway, the delivery time is of the order of 10 minutes. It's usually some multiple of 10 minutes. It might, it's half an hour, it's 3 times 10 minutes. If it's 25 minutes, it's 2.5. This kind of a rough thinking. And then a pint man could put away the order of 10 pints in a single setting. Okay, now what I want you to think for a moment is of a recurring decimal such as 1/3. So we can say something here. So you put in 1/3 into your calculator, it might give you something like this with the dot on top. And what that dot means is that the tree actually goes on forever and ever and ever and ever and ever. Okay. And then we can say a little bit more here. So the first thing here is actually 3/10. Think about that for a second. 3/10, yeah, 0.3 is 3/10. And the 0.3 is 300ths. And then you got 3 thousandths. Plus, go on and go on. So forth and so forth. So what you can say is stuff like this, that 1/3 is of order 3/10. Okay? And now that's kind of going with it's approximately 3/10. That's not too bad. The next one is probably more important. 1/3 is 3/10. That's the first bit. Plus terms of the order of 300ths. So a third is like 3/10, and then everything else after that is like a multiple of 300ths. Now, a multiple of 300ths is also going to be a multiple of 100. So what we see here is that 1/3, this is the last one I'm interested in, 1/3 is 3/10 plus terms of the order of 100. And if you look at the difference between the 3/10 and the 100ths, the 3/10 is big and the 100ths are small. So if you want to do an approximation, you can say something like this. 1/3 is approximately 3/10, because the other terms are a multiple of something small. Obviously, be careful with it. Okay, what have we got? There is something that we can show here just to be really ultra pedantic. All of the terms beyond 3/10 are individually less than 3/100. So for example, 3 over 1,000, that's less than 3 over 100. We can be more precise if we want. You can actually show that all the terms after 3/10, all of these add up to something that is a multiple of 300ths. I won't go into it, it's not too important, but you can show that all of these things added together are less than or equal to 10/9 of 300ths. And then I said, look, 300ths I'm not really interested in. 100, I know that's small. And you can show that all of these things added together are some multiple of, or actually what's important is less than some multiple of this. So we've kind of got this order of, initially it means it's approximately, but now we're really getting to the nub of it. Something is of order 1 over 100 if it is less than a multiple of it. So these things are less than 10/3 times 100. This becomes very, very important for us when we're analysing this error. Okay, so this is what we mean when we say 1/3 is 3/10 plus terms of the order of 100. It's 3/10 plus something that's less than or equal to something times this. And then this is what we wrote on the previous page. Because 100 is very, very small, we can say that something like this. Right, a more sophisticated way, which is really what I want, is not to worry about the constant being any particular size, but just say that x is of order y if x is, that says equal to a constant times y, really I want it to be less than or equal to. But of course the less than or equal to includes the equal, so I'm not too worried about the less than or equal to, or being less than. So really what you're saying is that it's some multiple of. And I think when we end up when we're finished, that's what I'm actually really interested in. Something x is of order y if it is some multiple of y. So we see some examples here. The area of a circle is of order r squared. Now, it's not important that pi is between 1 and 10 or anything like it. Now I'll tell you what the important thing is. Well, we'll see it in a second. So I've got some more kind of statements like this. The kinetic energy of a particle of mass m with velocity v is a half mv squared. The kinetic energy is of order m, it's a multiple of m, and it's also of order v squared, it's a multiple of v squared. The volume of the sphere is of order r cubed, and the period of a pendulum is, for example, of the order of the square root of L. What these statements are also are scaling laws. So if you talk about the area of a circle, and we're going to do it in a moment, if you double the radius of a circle, you do not double the area. The area, so a statement you might have heard, goes as the square, which means that if you double the radius of a circle, you end up, if you double r, where is it? If you double r, say it's 2r, you get 4r squared. So doubling the radius multiplies the area by 4. So you got the scaling. So this is kind of what we're talking about. We know that doubling the radius of a circle increases the area by a factor of 4. This is what we're reading because, okay, so let's write down, say we have an initial area A0, which is equal to pi, the 0 is just signifying for an initial, is pi r0 squared. Now, what happens if we send the radius to twice the original? We change the radius to r1. Now what will the new area be? The new area would be pi times the radius squared, which is twice r0 squared. And because the area is of order r squared, we get the squaring thing where it'll be 2r0 by 2r0, which is 4. You get pi by 4 by r0 squared, in other words 4 pi r0 squared, and of course pi r0 squared is the original area. So doubling the radius multiplies the area by 4. And then the interesting thing is if you halve the radius, it gets it actually multiplies the area by a quarter. So there's actually a good example of this is if the crust of a pizza isn't too thick, say you take a 16-inch pizza. Now almost everyone would say they could eat a 16-inch pizza. If you halve the radius to an 8-inch pizza, that quarters the area, so it quarters the size of the pizza. So what you actually have, and maybe we'll just write it up here, is that one 16-inch pizza, which of course actually is radius equal to 8 inches, has the same area as 4 by 8-inch pizzas. And it's funny, people don't really realise that because you can get a 9-inch pizza, and that's close to an 8-inch pizza, and you say, oh, I'll eat an 8-inch pizza. And if you think about it, like, oh, I'll eat that little pizza, and then I'll eat another one. Am I really going to be able to eat 2 more? Can I eat 4 pizzas? And the answer is you probably can, if you can eat a 16-inch pizza. A similar story goes with volume. Volume in general is, what the hell is this? In general of the order of the diameter. Oh yeah, I thought it was a footnote but of course it's diameter cubed. So for example, diamond is priced by numerous things, including volume. Well, it's mass, which is the same as volume if it's a uniform density. And look what happens when you double the dimensions of a diamond. So now I don't actually have a formula for the volume of a diamond. I just know that it'll be some constant times the diameter. And even the diameter, how do you define that? Well, I'm not going to worry too much about that. I'm just going to say that, say, the original volume of a diameter is some constant times, let's say, diameter cubed. And if you double the diameter, so this should be diameter by 2 cubed. And when you cube this, you get 8d0. You get 8cd0, which means that is now 8 times larger than the original. So this comes into play if you're ever buying diamond rings for yourself or for somebody else. The actual diamond themselves. So 1 carat